problem is called same tree. We are given roots of two binary trees P and Q, and we have to write a function to check if they are the same or not. Two binary trees are considered the same if they are structurally identical and the nodes have the same value. So in example 1, here we have the root of 1, so these are P and these are Q. And for the left and right children, we have basically the same values, so these trees are equal, and we just return true. Now for the second example, the roots are the same, but the first tree has a left node of a value 2, and the second tree has the right node of value 2, so the structure is not the same. The second tree is missing the left node, and the first tree is missing the right node, so they are not the same tree, and we just return false. The third example is pointing us to the same structure of the tree but different values. So in this case we have the same roots, but for the left node of the first tree we have the number value 2, but that value doesn't match the value of the left node for the second tree, so we just have to return false. The number of nodes in both trees is in the range 0 to 100, and the node values are from -10 to the 4th to the 10 to the 4th. So how do we actually how do we check if the trees are the same? Because it's free, and the most handy algorithm is DFS, depth first search, and the recursive approach. How do we define our recursive relation? So trees you can think of it as trees are the same if they have the same root. So let's P denote the root of the first tree, and Q denote the root of the second tree. If they are the same, and we also checked before that the left subtree of the P is equal to the right subtree, is equal to the left subtree of the Q, so P left is equal to Q left, and also the right subtree of P is equal to the right subtree of the Q. Then basically the trees are the same. So if we call the recursive function on the left subtree and we get the information that left subtrees in both are the same, and we do the same for the right subtree, the only thing that we have to check is if the roots are the same. So basically, if the root is the same and the left and the right subtrees are the same by calling the helper function, we know that by those three conditions the trees are also the same. Now for the time and space complexity, we will return early because we will be checking the smaller of those if they are not identical, smaller of the trees. So let's denote n to be the number of nodes in the smaller tree. That's the time complexity because we will visit all the nodes from that tree, and the space complexity is related to the recursion stack that we are using. If the tree is queued, so we have something like this, all the nodes on the left side, or something like this, all nodes on the right side, we will have basically the depth, the size of the stack will be n. So both time and space complexity are linear to the number of nodes of the smaller tree. The result of the main function in the same tree will be also the result of our helper function that will be called recursively. We will just pass the P and Q nodes. Note that we could also reuse the same tree function to call it recursively, but I found it's more readable to create a new helper function. So our helper function will get the root of the P, the first tree, and the root of the second tree. Then, because we will be calling it recursively, we have to have a base case. And for trees, most cases, the base case is basically checking if the either of the roots or one root is equal to null. And if it is, we check for the equality. Basically, they have to be both null for us to say that, okay, they are the same tree. And if they are defined, we will check their value. So basically, the root value has to be the same, and also the left subtree has to be the same for both the first and second tree, and the right subtree has to be the same. So we will just call the helper function recursively.